On this page, I'm going to focus on just the solutions of these equations. The table you can certainly fill in on your own. And I've tried to highlight here some of the odd equations, some of the weirder ones that we've seen. So like with most things, this is not necessarily what's going to be on the test. It's just to give you more practice. So the first one, you see that the issue is that there's no sine, cosine, or tangent in here, but really there is. If we were just to rewrite this, remembering that secant of x is really just a 1 over cosine x. Let me make this pen a little bit thicker. So we can rewrite the equation this way, and then we can solve that so that it's just cosine of x equal negative 1/2. So really this is just like the other problems we've done. It's just that you have a little more work to do to get the cosine of x part by itself. If you remember, our steps are to use our table and symmetry to get our first two solutions. So the table value is going to be x equals 2/3 pi, which if you have the table filled in, you should be able to just read that off. And then for symmetry, remember for cosine, the symmetry is that if you have one solution to a cosine equation, then another solution will be 2 pi minus that. So if I do 2 pi minus 2/3 pi, I'll get 4/3 pi as a second possible solution for x. So x could be 2/3 pi or x could be 4/3 pi. Then I can just write all solutions by just adding on multiples. By taking my original equation, my original solution, 2/3 pi, and adding on 2 pi k, or by taking the symmetric solution, 4/3 pi, and adding on 2 pi k. So that's all there is to this one. So the hard work was in getting the original equation to have the cosine separated. Part B is like the ones that we've done in class, but there's a pi in there, so that looks like it could be a little bit weird. So let's just use our convention of saying use a single letter like theta to stand in for the stuff in the parentheses, pi x, and then I can just go about this the way I've done all the other ones. So this equation is equivalent to saying sine of theta is 1/2, and then again I can read one value off of the table. The table says that if sine of theta is 1/2, then theta is 1/6 pi. Symmetry will tell us, again for sine, the symmetry is not 2 pi minus the angle I already got, it's pi minus that. So I subtract the first thing I got from pi, and I'll have 5/6 pi. So I will have a solution from the table and a solution from symmetry. Then I can write down all solutions in terms of theta. So theta will be 1/6 pi plus any multiple of 2 pi, or theta will be 5/6 pi plus any multiple of 2 pi. But of course theta is not really the variable in the problem. The variable is x. Theta was just standing in for pi times x. So I can go back and change the theta to pi x. Change the theta to pi x. And now to solve for x, I just have to divide everything by pi. So my final solution here will be that x is 1/6 plus 2k, or x will be 5/6 plus 2k. So even though it looks like the pi x is going to make things more difficult, this would be an x. In fact, because we have pi x in the parentheses, when we do our final solution to divide by pi, all the pi's are going away from the equation. So we actually get a pretty nice equation. Again, if you did want some particular values of x, you could just do that by using particular values of k. So if you figure out what these are for with k equals 0, k equals 1, k equals 2, you can plug those back into the original equation. You'll see that those are all correct. Part C, I'm not going to do the whole thing here, but I'll just point out that having the square in the problem means that you have to be a little bit careful. Again, I'm using theta is 2x here. So this equation is equivalent to 1 equals the tangent squared, but when I take the square root of both sides, I have to consider both the plus and minus case. The only time we haven't done that is when we're doing a problem involving like the Pythagorean theorem, where we know that the thing we're solving for, the variable we're solving for, has to be a positive number, has to be a length. Of course, tangent can the result of tangent can be plus or minus, so there's nothing about the problem that tells us that we should only look at the positive sign. So so it's similar to the ones we did in class from the My Math lab. This basically just breaks into two problems. You're looking for all the places where tangent theta is 1 and all the places where tangent theta is -1. And so really you just solve those as two separate problems. Don't forget that what's special about tangent is that for tangent you don't have to worry about symmetry. In other words, you don't have to take the table value and do anything to it. That's really the only value you need. And also with tangent, the period is pi instead of 2 pi. So there are two different things about tangent, but ultimately they make the problem have less steps. Okay, so let's look at the last problem, because this one will feel the weirdest probably, because this does not involve table values. For this we have to use our calculator. So first thing I do, of course, is have theta stand in for 5x, so I don't have to worry about the 5x at the moment, and then solve this so I have the cosine of theta by itself on one side. If you do that correctly, and you should take a minute to do it, don't just stare at my answer, do the algebra, but you should find out the cosine of theta is 2/3. If you start from there, then the calculator has to tell you the value of theta. Okay, you're not going to be able to do this from a table lookup. The way we do that is if you have to use your calculator, that's when you're using your inverse trig function. So if cosine theta is 2/3, then theta is the inverse cosine of 2/3. If you put that in, don't forget you should be in radian mode, you'll get theta is 0.8411. I'll just take it 4 decimal places so I have plenty of room. The symmetric solution, just like before, is going to be 2 pi minus that. So we need to do it on a calculator, and you will have to use your pi button. 2 times pi minus the answer you just got, and that should be 5.44, does that say 2? Okay, and again, I'm just giving myself more decimal places. I know I want 2 good decimal places at the end, so I'm making sure that at every step along the way I'm keeping at least 3 or 4 decimal places. So we're not really doing anything differently, we just aren't getting the exact answer. These are approximate answers, but again, if you put those answers back into this equation, you will find that those are about right. To get all solutions, again, I don't do anything differently. Oops. Say your theta, and I'll put approximately equal to, because I am rounding this. Theta is approximately 0.8411 plus 2 pi k, any multiple of 2 pi, or theta is approximately 5.442 plus any multiple of 2 pi. So again, I'm doing exactly the same steps, it's just that I don't know the exact value, so I'm using these decimal approximations. And once again, at the end, I realize that it's not theta that I have in my problem, it's really 5x. Remember, theta was just standing in for 5x. So I could replace the theta by 5x, and then I can get my solution for x. All I need to do is divide both sides by 5. So in the first case, I'll have x is approximately 0.168 plus 2 pi k, or in the second case it'll be x is approximately 1.088 plus 2 pi k. And so that'll be all my solutions for this equation.